So at the end of that last video, we said that a geometric series will converge if the ratio is between -1 and 1. We said, probably what we said and probably what was written down was that the absolute value of r had to be less than 1. Just notice that I don't think it was written out anywhere in that last video. The absolute value of r is less than 1 is the same as saying -1 is less than r, which is less than 1. So you could see either one of those. And a new phrase we need to know, -1 to 1, or absolute value of r is less than 1, is called the interval of convergence. R could be anything in between -1 and 1, and the series will converge. But if it's 1.00000001, if it's anything outside of those bounds, even if it's only a tiny bit outside of those bounds, the series will diverge. So the interval of convergence, it's an inequality that describes all of the, in this case, r values for which a series will converge. Okay, here for example 2, I want you to go to your textbook. This is on page 475, and then it goes on to page 476. This is example number 3, and there are 4 different geometric series given there, and it's your job to decide if the series converges or diverges. The way to do that, you're going to decide if r, the common ratio, the thing you multiply by each time to get the next term, is between -1 and 1. If it's not, the series diverges. If it is, the series converges, and you can use this formula that you promised me that you were in the process of remembering to find the sum. So why don't you try C and D? You could write in your answers here. All right, so here's a new definition. This was the title of 9.1, a power series. Something looks like a sum of an infinite number of terms, infinite number of polynomial terms, where the terms look like a coefficient. We're going to call the coefficients C's. So C0, C1, C2, all the way up to Cn, all the way up to, because it's an infinite series, C sub infinity. A coefficient times the next highest power of x. So I have C0 times x to the 0, plus C1 times x to the first, C2 is some number times x squared. You can see any kind of series that I can write and it looks like that, where the c's are some numbers, is what we call a power series. And then we call this a power series centered at x equals 0. Notice that if I wanted to center my series somewhere else, I would have, you can see it's written down here. Still the coefficients are the same, but instead of having a power of x, I would have a power of x minus a. So really that just takes having an x minus a, remember that's a horizontal shift to the right, takes a function or a series or a graph or whatever you want and shifts it a spaces to the right. Okay, so that second one is called a power series centered at x equals a. This, for example, is the nth term of a power series centered at 0. This is the nth term of a power series centered at a. And the number a, we sometimes, oh, I guess I just said it, we call it the center. So notice this. Here's the very most boring, plainest, the plainest power series. All the c's, all the coefficients are 1s. And so all I have is a bunch of 1s times the next power of x. So 1 plus 1x plus 1x squared plus 1x cubed plus 1x, okay, dot, dot, dot. This is a power series, and every geometric series is a power series. This one also happens to be geometric. What would you multiply every time? Well, multiply by every term. Multiply by every time to get the next term. In here, in this particular series, which is both a power series and a geometric series, r happens to equal x. Because x is the thing I'm multiplying by to get the next term each time. Well, this is super cool. because everything we knew about geometric series would apply, and it can start our conversation. It can start some of the thinking we'll be able to do about power series. If I know that r is between -1 and 1, which means since r is x, x must be between -1 and 1. If I can guarantee that I'm going to pick my x, so it's between -1 and +1, then this series will converge, and it's going to converge to 1 over 1 minus x. Remember that formula that we were remembering? It was the sum is the first term over 1 minus the ratio. Well, in this case, the sum is, what was the first term? 1 over 1 minus, what's the ratio? X. That's how I get this. This, you have to know this by heart, and this is the key to finding power series in so many places where you're going to need to find a power series. Watch all the cool algebra we're going to be able to do on this. I knew I was missing one line. Okay, so once you believe me, and I hope you believe me, do whatever you have to do to convince yourself. This fact we're going to use to write power series in a lot of places, because we're going to need to write a lot of power series in the next couple of weeks. And this process of taking a power series that you know, and the thing you know it adds up to, and tweaking it so it works in a new scenario, we just call that transforming the series. A lot of techniques you know for transforming integrals or equations, they're going to apply. So like I said, watch all the cool algebra we can do. So I have this big star up in the corner to help us remember that the key to most of our work here is going to be remembering that the sum of an infinite series, of an infinite geometric series, as long as the ratio is between -1 and 1, is the first term over 1 minus the ratio. So if you find it convenient, more convenient, that's the same as saying, in this case, I want powers of x, so I'm going to use x for r. That's going to be the first term over 1 minus x. So think about what this means. Ooh, wow, it's cool. There's a lot about what this means. So if I had some function, 1 over 1 minus x, and I thought that that function, it's kind of hard to work with. Maybe it might be difficult to graph, it might be difficult to find a derivative of. If it's somehow inconvenient, I can replace it legitimately, algebraically replace it anywhere I want, anytime I want, with this series. So that turns out to be really convenient, because look at that series. It's a big polynomial, and polynomials are our favorite functions to do calculus on. They're the easiest to take derivatives of. They're easiest to find antiderivatives of. So anytime we're able to find tricky, complicated, ugly functions that we wish we could do calculus on, if we could find a power series to replace them, we can do the same calculus on that power series, which is probably going to be easy calculus, and we can skip the difficult calculus on our complicated expression. So that's the reason, that's the motivation here. And we'll do some graphing in class tomorrow so that you can be convinced that 1 over 1 minus x, that rational function, is actually completely equivalent to the sum of this polynomial series. Okay, so look at part A. I want to find a power series to represent a slightly different, because we're, baby steps, a slightly different rational function. So there's a couple ways you can go about this. It comes a lot easier with practice. I'm going to compare this function that I'm supposed to rewrite with the thing I already, I'm going to compare it with this one I already know. What's the difference between 1 over 1 minus x and 1 over 1 plus x? That's the same as 1 over 1 minus negative x. And that's what I would get if I had to sum an infinite geometric series with r equal to negative x. Look at this. This is the first term would be 1, and 1 minus, what do I really wish this was? I really wish it was 1 plus x, because I want to make this denominator, but I need to make it fit into this formula, so 1 minus negative x. That's a negative x. So watch this. That's going to be the first term of 1, and every time I need to multiply to get to the next term, I'm going to multiply by negative x. So the next term is going to be plus negative x. I'm going to write minus x. The next term is going to be negative x times negative x, which makes positive x squared. The next term, I'm going to multiply by negative x. That's going to make minus x cubed. Plus x to the fourth. And you can probably see how the pattern's going to go. Minus x to the fifth. Plus dot, dot, dot. There's my power series. That, if I had to add it up, it would add up to 1 over 1 plus x. Okay, so look at example B. Now that I have a series for 1 over 1 plus x, let me write that actually. So that power series I wrote, 1 minus x plus x squared minus x cubed plus x to the fourth minus x to the fifth plus dot, 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 going on forever, ever. That's exactly equal to, so I'm going to write an equation, is equal to 1 over 1 plus x. As long as I promise that x is between negative 1 and 1. And I'm not going to mess with that for now. I promise. I'm not going to break that rule. Okay, so look at this guy. Once you believe this is true, what would I do to that expression I just circled to turn it into this new expression? Well, looks like I have to multiply by x. So I can multiply term by term in my power series to get a new sum, which is equal to x over 1 plus x. So if I wanted, you could think of it this way, multiply both sides of the equation by x. My sum is going to turn into x over 1 plus x, because I multiplied the right-hand side by 1. So, sorry, I multiplied the right-hand side by x. So watch what happens when I multiply the left-hand side by x. It's going to be 1 times x is x, minus x times x makes x squared, plus x squared times x is x cubed, minus x to the fourth, plus dot, dot, dot. So there, on the left, if you type this into your calculator, x minus x squared plus x cubed minus x to the fourth plus dot, and you kept going, I don't know how many terms, 5, 10, 15 terms, and you graphed this at the same time, they would be indistinguishable. At least for the places where x is between negative 1 and 1. Like I said, we're going to do some graphing in class tomorrow to help you believe that. Okay, so what if I need a power series to represent 1 over 1 minus 2x? So go back to this guy. Oops, I was trying to circle that. What should I replace that x with? It looks like I need to replace it with 2x. I have a first term of 1 and a ratio, a common ratio of 2x. So let's try it. First term 1, I'm going to multiply by 2x to get 2x, plus I'm going to multiply by 2x again, that's going to be 4x squared, plus I'm going to multiply by 2x again, it's going to be 8x cubed, plus dot, dot, dot. That is my power series, and I'm claiming that it's equal to 1 over 1 minus 2x, but let's clear some of this stuff out of the way. I might regret later that I cleared that out. It might be useful to good. Okay, so let's prove that it's actually equal to that sum. I'm going to use this statement. I know my sum is going to equal, the first term is 1 over 1 minus, what was it that I was multiplying by each time? 2x. So sure enough, as long as x is between negative 1 and positive 1, 1 plus 2x plus 4x squared plus 8x cubed plus 16x to the fourth plus dot 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 is going to equal 1 over 1 minus 2x.